Okay, so this is our last part for 5.1, and this is all really going to be examples so that you're able to do the homework. Um, so in the last video, recall that our left endpoints were, we called them L of n, and we did it using some notation, but for this section in the book, we will just, or for most of these problems in the book, we're going to just write them out because for the homework, I gave you n's that were pretty small, but I just wanted you to know that if we take n very large and make it shoot off to infinity, we get a better approximation, which we'll talk about in detail in 5.2. So for our left endpoints, we did L of n. And when we do our left endpoints, we start off at the left of the interval, so at the very beginning of the interval, which is f of x naught, so, and then times our delta x, plus f of x2 times delta x, times plus f of x1 times delta x. And then we're going to go all the way to f of x of n minus 1 times delta x, because we're just taking the leftmost endpoint. Okay, and after that, we also learned our right endpoint, which is r of n. And for our right endpoint, instead of starting at f of x equals 0, so our starting point, we would do f of x1 times delta x plus f of x2 delta x plus dot 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 all the way to f of xn and delta x. And these divided our initial interval into n sub-intervals. So what do I mean by that? And maybe I should have drawn this earlier, but we don't know, let's say we don't know what the graph is, and this is our point x naught, which is, remember, equals our a, so our very end. And then our xn here is equal to our b, so from a to b, our interval. And so if we're starting off with our left endpoints, we're going to start off here and take it all the way to the function and draw that rectangle there. Same thing, but for our right endpoints, instead of starting here, we're now starting at x equals 1, which is going to be a plus that spot here, and draw that rectangle here all the way till we get to x of n, which is equal to our ending interval. So now let's go ahead and do an example. So for an example, we're going to estimate the area under the curve of f of x equals 1 over x from x equals 1 to x equals 4, or the interval 1 comma 4. And so we're going to do this using two methods, our right endpoints to get practice, and then we'll do it again using our left endpoints. Okay, so the first thing that you want to do is you're going to want to find the width of each of your rectangles, because those aren't going to change at all. But before we do that, what's going to help you find the width is, in the last video, I drew the graph so I can show you what it means to take a right and a left endpoint. But for this function here, you don't necessarily always have to draw the graph. So let's draw the graph of this just to get my point across here. But then I'll show you a way where you won't always have to draw the graph of the function. Not necessarily. Oh no, I almost had it great. I hate when I keep that button on. Okay, so this is our graph y equals 1 over x. And remember that at point 1, 1, we are at 1, 1 here. Okay, let's just say it's right there. And then let's say x equals 4 is over here. So we said, okay, if we're doing our intervals, what we're going to do is we're eventually going to want to partition our interval from 1 to 4 into, oh, I didn't give you an n. Wow. So okay, let's do here n equals 6. So we eventually want to partition our graph, our interval from 1 to 4 into 6 partitions, so 6 sub-intervals. And so in order to do that, we need to break this up. And recall that our delta x, which is our width of each of our rectangles, is always going to be b minus a all over n. So you're going to take your left minus your right endpoint, and then you're going to divide it by how many intervals we want. So in this case, we're going to do 4 minus 1 divided by 6, which is just 3 over 6, which is the same thing as 1/2. So our intervals are going to be cut into 1/2. Now we could go ahead and go, okay, let's cut this like this, you know, and just draw these rectangles and then figure out where it's overestimating, underestimating, and, you know, go about that. But what if the graph doesn't, I mean, this graph is already getting a little out of hand because it's so small and detailed. What if we don't want to draw the graph, or what if we don't know the graph and we just want to, you know, graph the endpoints? We don't want to have to graph each function each time. Well, you don't really have to. Those were really just for demonstration purposes. And in reality, you shouldn't need to draw the graph at all. What you want to do instead is you want to actually, what will help you if you need the graph is to draw a number line, because a number line might help you visualize what's happening with the right and the left endpoints. And I would always start the number line where your A is. So our A is 1 and our B is 4. Okay, perfect. So now from here, what you want to do is, now that we know that our width is going to be 1/2, what you're going to want to do is now you're going to want to cut this into 1/2 pieces. So what do I mean by that? So if I add 1/2 to 1, I'll get 1 and 1/2, which is the same thing as 3 over 2. If I add another half to that, I'll be back at 2. Well, that was ugly 2. And then if I add 1/2 to 2, I'll be at 2 and 1/2, which is the same thing as 5/2. And you could keep it as 2 and 1/2. I just want to keep write it as a mixed number because I know I'm eventually going to have to plug it in. And then after that, I'll get 3. And then I add another half to that, and then I'll get 3 and 1/2, which is the same thing as 7 over 2. Okay, and so this tells us, once we are able to break it up, these are our individual sub-intervals. So we have one sub-interval here, another here, another here, another here, another here, and another here. And I know what you're thinking. You're like, okay, there's 1, 2, 3, 4, 5, 6. Oh, look it, that's our n. So we exactly have 6 sub-intervals, which we should have. Okay, so now what we're gonna want to do with this is we want to find our right endpoints. So in order to do this, what I would recommend is that you label these when you're first doing these until you fully understand them or get a hang of doing these problems. So my first spot is my x naught, because remember that's the same as a. And then this is my xn, which my n value is 6, which is the same thing as my b value. And so this means this is x1, x1, x2, x3, x4, x5, and then x6. So that way, when you're actually plugging them back into your left and your right endpoints, you can easily input them and know which one you're inputting into what. Okay. Or you could also do a table, because that might help you. And I'll show you how to do that table in just 1 second. Okay, so I'll show you both ways, so you have those tools available. Okay, so if we're doing A, which is to find the right endpoints for the right endpoints, what we're going to do is that we know that if we have our right endpoints, we're going to label that as R of 6, 6 because we have 6 sub-intervals. That's our n value. So if we do our right endpoints here, we're starting off at f of x1. Here our f of x1 is 3 over 2. But for now, I'm just going to leave it as f of x1 times delta x, just to show you. Then we're going to go on to f of x2 times delta x plus f of x3 delta x plus f of x4 delta x plus f of x5 delta x, and then very last one, plus f of x6 delta x. So remember, we started off here, and now we need to go to the very end, because we have to make sure that we're summing up 6 rectangles. Here we have 1, 2, 3, 4, 5, 6. So perfect. We have 6 intervals. And now what we're going to want to do is we're going to want to evaluate f of x1, f of x2, f of x3, and all the way to f of x of 6. Okay, so to do this, what you want to do is recall that our function here is f of x is equal to 1 over x. So this tells us that if f of x1 is 3 over 2, if I plug that into my function here, f of x is 1 over x, you'll be plugging that into each one of them. And so this one here is going to be f of 3 over 2, which is equal to 2 over 3 if we plug it into our function up here. Okay? And so you could, if it's an easy enough function to just plug it in and, leave it at that, then go ahead and do so. This function is. But if it's not an easy enough function, like you could just plug them in if you know them, right? I could already tell this is going to be 3 over 2. This is going to be 2 over 3. This is going to be 1/2. This is going to be 2 over 5 because I have an easy enough function. But what if you don't? What I would probably do is make a small table just so you don't get confused and say, okay, my xi's or my xi's are going to live up here. And so here is going to be x naught. X naught where it is 3 over 2. You don't have to do that each time. So your little x subscripts are going to live on top. And then after that, what you are going to want to do is put in all your xi's. So 1, 3 over 2, 2, 5 over 2, 3, 7 over 2, and then 4. And so you don't have to do this table. You could have easily found them out and wrote them out over here in this little line graph and just done it directly under. But just to keep things organized for those of you who like tables, here's one way that you can organize this craziness. And so then our f of xi's are going to live here. And so if I plug 1 into my f of x, I'm going to get 1 over 1, which is 1. If I plug in 3/2 into 1 over x, I'm going to get 2 over 3. Here I'm going to get 1/2. Here I'm going to get 2 over 5. Here I'm going to get 1 over 3. Here I'm going to get 2 over 7. And here I'm going to get 1/4. So now when I want to plug it into my into my right endpoint, I can easily just look at the graph and go, okay, this is going to be x naught, x1, x2, x3. I guess I should have labeled these two, right? x4, x5, x6. And so for my right endpoint, we always start here for our right endpoint. So then it's going to be So then it's going to be f of x1, which is right here, 2 over 3. So it's going to be 2 over 3 times our width, which our width is always going to stay the same. We found it up here, is going to be 1/2 plus 1 over 2 times 1/2 plus 2 over 5 plus 1/2 plus 1 over 3 times 1/2 plus 2 over 7 times 1/2. And then the very last one is going to be 1 over 4 times 1/2. Okay, so all we did here is we multiplied our width, which is 1/2, and then we are multiplying it by the height of the function. And so each time we're doing that, we're getting areas of rectangles. And now we can easily simplify this. This one here will simplify to be 1 over 3. The 2's just cancel. This is going to be 1/2. This is going to be 1 over 5. This is going to be 1 over 6. And then what? Plus 1 over 7. And then plus 1 over 8. Okay. And now what we're going to want to do from here is that we're going to just add them up and find that approximation. Now I calculated this ahead of time to save me time on the video, but just input them on your calculator and then you'll get 1.217857. And now this is really cool because now if we wanted to do the left endpoint, which I'll do on the next page, which we'll do on the next page. I'm just going to copy and paste this over so I don't have to write it again. Hopefully you still can see this, or you can flip the page. So for our left endpoint, we will write L of 6 to tell me or whoever's reading your paper that we're dealing with the left endpoint. And so remember, for the left endpoint, we're going to go from f of x 0 to our delta x plus f of x1, delta x plus f of x2, delta x plus f of x3, delta x plus f of x4, delta x. And then here we're going to stop at x of x5 delta x. One way you know that you stop there is because we already have 6 squares here, but also remember, because we started on the left-hand side, we counted this one. We don't have to count this one. We will still have 6. And remember that for our left endpoints, we always will end 1 before. Just like for our right, we start 1 ahead. And now if we do that, this one's nice and easy because we already have that chart. We're going to look here for our first endpoint, and we're going to go, okay, this is going to equal f of x naught. F of x naught is just 1 times 1/2 because of my width of each rectangle, plus 2 over 3 times 1/2 for x of 1 times delta x, plus f of x2, which is 1/2 times my width, which never changes. And then this is going to be f of x3, that's right here, which is 2 over 5 times 1/2, plus f of x4, which is 1 over 3, and it's 1/2, and I ran out of room, plus our last one, which is 2 over 7 times 1/2. And now you can simplify it and add it all up, but I did it ahead of time, which is 1.59285. Okay, so remember that this function was actually a decreasing function. I deleted it, but it was a decreasing function, look like this, from the part where it hit 1 to 4. It was decreasing here. And so it makes sense that our left endpoint is actually larger than our right endpoint because it's a decreasing function. And recall in the last video at the end, I said that if you have a decreasing function, your left endpoints will always overestimate and your right endpoints will underestimate the function. And that's because when we draw our rectangle starting from 1, we hit this spot here and then we go over, and so we get that overestimation. And then for our right endpoints, we actually start here and then move this way, so that's going to cause that underestimation. And so for the next problem, we're going to do the distance problem, and there's a couple of those on your homework. Okay, so now we're going to move on to the distance problem, which the distance problem, what we're trying to do here is we're trying to estimate the distance traveled, or we can also find the displacement of an object moving in a straight line over a period of time. And so for distance travel, that one's pretty self-explanatory. So if you're driving on the freeway on an average of, like, let's say 60 miles per hour, you want to know after some time how far did you go. Now, your average is about 60 miles per hour, but it doesn't mean that at every second you were actually going 60 miles an hour. What if at sometimes you were going 70 or sometimes you were going 50? So the distance problem allows us to estimate that distance given that you know your velocity at certain time steps for your function. Now, the most accurate thing would be that if you knew every millisecond, you would be able to get the exact distance. But I mean, it's not a bad estimation if you can check it every, let's say, 2, 3, 4, 5 seconds. That's still not a very bad estimation of how far you went. Now, for displacement, I want you to think of, this is more probably like a physics problem or maybe even a chem problem, where if you're displacing something, you're dropping something, and you want to know the distance that thing went, as long as it's moving in a straight line, then you can estimate how long or how far it went. So that's exactly what we're going to do in this section. So let's say you want to find the distance of something traveled over time. What you'll do is you'll be given some time steps. So some time step here. We'll call it time, and we'll call these time steps Ti for every time step. And now from here, what we want to do is we're going to also be given the velocity at that second. So we'll say that velocity is equal to v of Ti. And so our first time step we'll call T naught equals 0. Oh, sorry, we'll just call it T naught, not T naught equals 0. So we'll call it T naught, but it should equal 0 because at first that first time you're not, at the first second you haven't really started yet. So at time equals 0, you do need that initial condition. So maybe I will leave it there, but I'll leave it higher up. Then we'll get T1 for the second time step. Now the second time T1 could equal anything. It could equal 1 second, equal 2 seconds, 3 seconds, 4 seconds. It doesn't really matter. And then we'll get T2, and then we'll go all the way to the Tn time step. So whatever time step you're ending in. And then for our velocity, we want to know the velocity at that specific time. So we'll always get these values, v of T1, v of T2, all the way to v of Tn, because we want to evaluate the velocity at that specific time. So how fast are we going at that time? So this here is going to tell us how fast we are going. How fast we are going, and this is our time steps. Okay, perfect. And so here are what we are wanting to do in this section. We were talking about the area under the curve and how we can use left and right endpoints to find the area under the curve. But here we're kind of doing a distance problem that really doesn't feel like we have anything to do with area under the curve, but in reality it does, because you want to know, okay, what's the overall distance? Because before, when we had derivatives, we were just given the position function and then took the derivative of v of t. And v of t only gives you how fast you're going for a specific time, or if you know the time, you can tell how fast you were going for that specific time. But now here we want to know overall what that velocity is. So it actually ends up being the same problem as area under the curve. You want to know, if you are given a velocity over time, can I find that distance? So here, instead of using delta x, we're going to be using what's called delta t, because our change is now happening for our independent variable delta t. So here we're going to say that delta t, our change in t, is going to be ti, so a time step minus the previous time step, which makes sense. So all you're doing here is, let's say for instance this time step was 15 and this time step was 5. So your delta t between these two times is just 10. And for the most part, you want to keep these distances consistent. So if this distance is 0 and this distance and t1 is 10, then you want to keep this 20. So you want to keep that delta t, that width of time, or that interval of time from when you're checking each velocity, constant. And so that's how we'll find it, by just subtracting the one before minus this one, so that we can get an accurate time, because it doesn't make sense to go backwards in time. So it'll work out. And I'll show you an example. So then we can approximate the displacement, or distance, on the interval by, we're going to do v of ti minus 1 times, let me do a big X, delta t. Or we could also do it by v of ti times delta t, depending if we're which one we're using, right? Left or right endpoints. So we can actually do both of them on this scenario. So what this is saying is that if you want to know the distance, how far you went at a specific time, right? What you're going to do is you're going to take your velocity, how fast you're going, and multiply by the amount of time you spent with that velocity. So for example, if at t equals 1, let's say we're at 5 seconds. Let's pretend we're at 5 seconds. And here you're going, I don't know, 20 miles per hour. Well, within this time step, you can calculate the distance by going, okay, well, for 5 seconds, I was going, okay, probably not 20 miles per hour, but let's say 20 miles per second or something, right? How fast did I go? You would multiply that value, or that velocity, times that second, so that you can see how much and how far you traveled, which makes sense, right? I'm sure you guys have done this before. If you've driven before, you can calculate how long it's going to take you to get somewhere based on how many miles it is and how fast you drive, right? You usually do that division to tell you how much time it'll take you. Well, now we can work backwards to actually figure out the distance you went, given how fast you went and how long it took you. And that's all that is. So what we're going to do is we'll multiply it. And hopefully this makes more sense when we do an example. And so the total displacement over the time interval between 0 and t of n is going to equal the sum of all of them. So for example, you want to know how far you went over that series of time. You can start here and you can multiply these two together and then add the next ones, all the way to before. Or you can start at t1 and go all the way towards the end. And so what that leads us to is that we can calculate this two ways. That first way is by doing d is approximately, and I'm not going to say it's exactly equal to because it's not, is v of t naught times delta t, so that we can know how far we went at the initial time, plus v of t1 times delta t, plus dot, 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 v of tn minus 1 delta t. Okay, but this is only for your left endpoint. So before, when we did the Riemann sums, we were able to calculate left and right-hand sided endpoints. And now we could do the same thing with a velocity problem. So that's exactly what we're going to do. And so now you could probably take a guess at the next formula we'll go over, which is it's going to be the exact same thing, except we're, instead of starting at v of t naught, we're going to actually start at v of t1. And then we're going to multiply by delta t plus v of t2 times delta t, all the way until we hit our v of tn v of tn times delta t. And this is going to be our right endpoint. Right endpoint. Okay, beautiful. And so basically what it's saying is that you can start calculating your distance by starting from the left endpoint, which would be this equation here, and go, okay, I could start here, multiply, get this, go all the way to the one before this one, and then that'll approximate my distance. Or I could start at t1, ignore this one, and go all the way until my very last one. Okay. But here's the thing is that when this tells us our displacement and our velocity, we want to make sure that when we're dealing with velocity, we are doing the absolute value. So when dealing with velocity, because these problems are, you can use them for displacement and you can use them for velocity. And you'll see in your book that you can use this formula many different ways depending on the word problem. And so with velocity, I want you to use the absolute value of v of ti, so that we make sure that at that specific time, our velocity is positive, okay? So that we can find that distance. Because if we get negative, then we might be taking away that distance, and we don't want to do that. We want to keep positive. Okay, so for example, so let's do a quick example, and that'll be it for this video, because I think after this example, I think you guys got it. If you don't, please let me know. I could probably make another example, but email me, and I'll be happy to make another video with more examples if you need to. So the speed of a particle every 5 seconds over a period of 30 seconds. So let's say you're given the speed of a particle every 5 seconds over a period of 30 seconds. And so if you're given the speed, most likely you'll be given the problem in the form of a table. So the time in seconds is going to be here. And then here I'm going to do velocity in meters per second. And this is going to be our VIs. me draw a straight line. Do a few. I think I might have done too many, but it's okay. Okay, so let's say that at the first time we're at 0 and we're going 50. 5 seconds pass, and now we're going 60. 10 seconds pass, and then we're going 65. 15 seconds pass, and then we're going 62, so we decrease. 20 seconds pass, and then we're going to 60. 25 seconds pass, and we're going to 55, and then 30 seconds pass, and then we're going to 50. So what I want you to do here is I want you to approximate the velocity, the distance based on this information. So what we're going to do is let's actually do the left and the right-hand sided endpoints. So to calculate our left endpoints, we would do, since we're dealing with velocity here, we'll do v of t naught times delta t plus, I hate when my writing gets ugly, v of t1 delta t, and then we'll go all the way until we get v, the absolute value of v of tn minus 1. Oh, and in this case, our n minus 1, actually, we want to write it for this specific problem, is going to actually be on, let's see how many intervals we have. We have 1, 2, 3, 4, 5, 6, 7 intervals. And so we're doing the left-hand sided interval. We're going to stop at this spot here. So that means we're going to stop at v of t6 times delta t in absolute values. And so now to get them, what we're going to do is we're going to do, since we noticed that first we need to actually calculate our time steps, our delta t's. The nice thing about this problem is they gave it to us. Here they said every 5 seconds. So this tells us that delta t is equal to 5 seconds, and we're already in terms of seconds. So that's perfect. We don't have to convert or anything. Sometimes you will have to do that. But if you didn't know the time steps, what you could do is go, okay, if I do this time step minus the previous time step, that gives me 5 seconds. Similar if you do it here to this. You'll always be given something where the time steps are going to be exactly the same, so you don't need to worry about that. So 15 minus 10, that's 5 seconds. 10 minus 5, that's 5 seconds. I'll always give you something like that. I won't give you something wonky. That's not very fair. Okay. Moving on. So now what we can do is, since we're calculating that left endpoint, we're going to actually go v of t naught times delta t. Our delta t's are always going to be 5. That's not going to change. And we're going to do v of t naught. V of t naught is 50. And then our delta t here is going to be and then our delta t here is going to be 5 seconds. So that's not going to change. Okay, so now we're on the same. So now that we're on the same page, all we're going to do is we're going to start here and multiply it by our delta t. So the first one's going to be 50 times 5 seconds plus 60 times 5 seconds plus 65 times 5 seconds plus 62 times 5 seconds plus 60 times 5 seconds plus 55. That looks like a 35, but it's a 55. What? Sometimes, I swear. 55 times 5 seconds. And this is going to give us the approximation of our distance over that series of time. So if we multiply this out, when I did it ahead of time because I don't want to be plugging this into my calculator, is we're going to get 1,760 meters. So overall, in the time of 30 seconds, we traveled this far. Okay, and now you could do the exact same thing for the right endpoints, which I probably won't do in this video because I want you to give it a try. For the right endpoints instead, I'll give you a hint, is your right endpoints, instead of starting at V of t naught, you are going to start at V of t of 1 because you're starting with the right endpoint. And then you're still going to do delta t. Delta t is not going to change for this problem. It's specifically 5 seconds. It doesn't have to always be 5 seconds, but for this problem, it is. And then we'll go to the absolute value of v of t2, delta t, plus dot, 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 all the way to v of t7, delta t. And that's because for the left endpoints, we go from this point here all the way here. But for our right endpoints, we're going to go from here all the way to the right. And now I will give you the answer for this one. If you plug it in, you'll actually get the same answer as this one here. And this is actually just a coincidence, just because our starting speed here was the same thing as our ending speed. But if it wasn't, then you would get a different answer for this problem. So you'll get the same answer as before. So try it on your own, getting practice with these problems. You do have a few homework problems, so you should be okay. Again, as always, I'll be on Zoom during our regular class time and more than happy to help you. Please reach out to me. I've had a couple students already reach out to me and come into my Zoom session asking for homework help, and I love that, because if not, I'm just on Zoom staring at my computer waiting for someone to log on, and that's kind of boring for me, and I really want to help you as much as I can. But I do understand, like, and some of you guys are busy with your siblings and stuff, but keeping that open communication with me too. And also want to mention something about the homework. I did notice, not this last homework, I haven't started grading this last homework, but the last homework assignment, a lot of you guys didn't turn it in. And so if there's a reason that you couldn't turn it in, please let me know. Usually I don't accept late work, but these times are a little bit different. I can't really expect the same from you. But if you need help or you need like a day or two extension from the homework, you have to let me know. I totally understand that it's so much harder to work from home. I'm struggling with that too. So please, please, please let me know how your homework's going. I give you deadlines just to try to keep you structured, and I want you to try to keep those deadlines always, but I also don't want it to come to the cost of your grade, because as long as you're putting in the effort for me and trying your best, that shows me that you do care. And it's not that you don't want to learn this. You're still responsible for understanding and knowing all this information, because remember, most of you are moving on to Calc 2. So understanding all of this is crucial for Calc 2. I'm not going to stress this enough. And I won't pass somebody if I feel like it'll hurt them if they move on to Calc 2. But I really want you to try and work really hard, but just keep an open communication with me, because I can't help you if you don't let me know that you need help. So I appreciate those who are reaching out to me and saying, hey, Ms. Gonzalez, I couldn't finish the homework yesterday because I had to take care of my little brother or sister. Is it okay if I turn it in tomorrow? Yes, that's fine, but let me know so I don't just think that you're just not doing your homework. I don't ever want to think that from any of my students. I always believe that you guys are doing the very best you can, but again, you have to let me know. And this goes the same way for other professors, is maybe, I'm sure they're very understanding too as well for these times, that it's not that easy. And I'm sure your professors are struggling themselves trying to adjust to this online learning. So please, not just for my class, but for all your other professors, reach out to them and say, hey, if you're having trouble, let them know, because if you're having trouble, let them know, because it's important that they know what's going on, because they can't help you if they don't know, right? So please keep me updated, and I hope you guys are all staying safe, and I'll work on the 5-2 video in just a second. Okay, bye, see you in the next video, or on Zoom, hopefully.